Welcome to this slightly impromptu video on the expected value and variance on of normally distributed random variables. All right, so let's take a continuous random variable that is normally distributed. Right. So let's say we have a x that is normally distributed with mean mu and standard deviation sigma. All right, and let's say x is equal to sigma set plus mu. So what we've done is we've taken the standard normal distribution set that has mean 0 and standard deviation 1. We've scaled it up so the standard deviation becomes larger, and then we've translated it by mu to move it to the right position. All right. So this is how you can use the standard normal distribution to create all other normal distributions. All right. So what I want to do now is I want to make sure that this construction actually has the correct properties. Right. The first thing I'm going to do is I'm going to write an expression for its probability density function. All right. So the probability density function is going to be 1 over sigma square root of 2 pi e to the power of minus 1/2 x minus mu over sigma squared. Hopefully I did this correctly. And what this really is, it's actually just 1 over sigma times the standard probability density function of x minus mu over sigma. All right? Beautiful. So that's the probability density function. The next statement I'm going to make is on the linearity of the expected value. All right? So the expected value of x is going to be, well, it's going to be the expected value of sigma set plus mu. So it looks like a 2, but it's not. I'm just slightly lazy. Let's put a line through this for good measure. No, nobody thinks it's a 2 or a 7, hopefully. But since the expected value is linear, what I get here is I just get sigma times the expected value of set plus mu. And the expected value of set, well, it's symmetric about the y-axis, so this is actually just 0. So I get the correct mean. Beautiful. That's something, at least. Okay, and I also want to make a statement on the variance of x. It's going to be the same as the expected value of x squared minus the expected value of x squared. I might have to flip these terms. I can never remember if the square is outside or inside. Probably if there was not, never mind my main topic of investigation. And in this case, what it's actually going to give us, it's going to give us sigma squared times the expected value of x squared or something like that. But it ends up canceling to 1. So the variance is sigma squared, or the standard deviation squared. But when I want to find the standard deviation, what I have to do is I take the variance and I take the square root, and I get the correct variance. So what I've done is this construct that I've made here actually has the correct attributes that I want my normal distribution to have. So that's good news. All right, so let's start with the first one. Okay. I will start by noting that the cumulative distribution function of x is the same as the probability that x is less than small x. Well, this is the same thing as the probability that sigma set plus mu is less than x, which is the same as the probability that set is less than x minus mu divided by sigma, which is the same as the standard normal cumulative probability function of this thing. All right. So I can always write any normal distribution, it's CDF, as the standard CDF, just shifted and scaled. All right. And now I can use the fact that my f of x is actually just the derivative of the CDF. Well, it's the same as this differentiated. So that's dx of this beauty here. Well, I have to use the chain rule here. I have to first differentiate the CDF here. But what happens when I differentiate the CDF? Well, I get the density, the PDF. So what I get here is I get phi of x minus mu over sigma. And now I have to differentiate the inner function. Well, if I differentiate this, it's just x over this. So I get 1 over sigma. Wasn't that pretty beautiful? That wasn't that bad. That was the first statement, the blue statement. Not too shabby. All right. Okay. It's all the way over here. Let's try the next one. So the expected value. Show the linearity of the expected value that it actually gets us the same thing. All right. So the expected value of our random variable is it's defined as the integral of x times f of x dx. All right. Okay. But this I've just shown is the same thing as the integral of x phi of x minus mu over sigma dx. All right. Now I make a change of variables. I say x is the same as sigma times set, small set, plus mu. All right. So what I get here is I get the integral of sigma set plus mu of phi. And if I put this into this where the x is, the mu's cancel, and then I divide by sigma, and what I end up with is d set. Isn't that absolutely gorgeous? All right. Ooh, I'm missing. What am I missing? I'm missing the sigma. 1 over sigma here. All right. But when I actually let's move this to a better place. Let's move it out here. Because when I make this change of variables, I also have to change the dx to a d set. And when I do that, that actually absorbs this 1 over sigma thing. So this is actually what I end up with. All right, now I can use this beautiful linearity of the integral to say, well, this is the sigma of set phi of set d set plus mu times the integral of phi of set d set. All right. This is the definition of the mean of the standard deviation. The variable times the density, the PDF of the same variable, and we integrate. Now this is mu times the integral of the PDF over the whole interval. Well, if you integrate the PDF over a certain interval, you get the probability that the variable is in that interval. So if we integrate over the whole interval, this is actually just 1. And what we're left with is the mean. Beautiful. I did this with the normal distribution that is written in terms of the standard normal distribution. You can do this with any linear combination. The expected value is linear. So even if it wasn't this, but it was some kind of other linear combination, this argument would still hold up. All right. And if it wasn't a continuous random variable, if it was a discrete random variable, all these arguments still hold up. You just exchange the integral for a sum. And the PDF here you just exchange for the probability function. And it actually is the exact same argument, pretty much. You still just use the linearity of the object that you're using. I just think it's wonderful. All right, let's try to do the last one and see if we have time for that. So now the variance. This is actually pretty interesting because the variance, the fact that you can write the variance in this way, plus minus this, I might have to flip these again, I think it's just wonderful. So what is the variance? Well, the variance of x is, well, it's the integral of x minus the mean squared and then the PDF. Right? But this is exactly the same as, let's just write it up here, the expected value of x minus mu squared. Right? X minus mu squared. Boom. Whew. All right. Let's continue with that. Now we can actually use linearity that I proved with the green. Almost soon. So let's expand this parenthesis here. So I have x squared. That's looking good so far. Minus 2 times mu x plus mu squared. All right? And now I can use the linearity of the expected value. This is the expected value of x squared minus 2 times mu expected value of x plus mu squared. The expected value of a constant is the constant itself. All right? Mu is the expected value. This, and this, it's the same thing. It's two ways of writing the same thing. All right? So what I have here is I have the expected value of x squared minus the expected value times the expected value squared plus the expected value squared. So I have minus 2 times something plus the same thing. What I'm left with is just one of that thing. And I'm slightly amazed that I actually remember that in the correct order. I have no mechanism to remember this in the correct way. I've never developed it because it was absolutely not necessary at any point. Okay, so this is the formula for the variance for a random variable. All right, so let's see if we can use that to calculate the expected value of x from the standard normal distribution. All right, so now we can use and actually use the green result here. So let's should we measure? This is green because I used the green formula. So let's see if we can continue this. So now we get this is equal to the expected value of sigma set plus mu squared minus expected value of sigma set plus mu squared. All right, and we already showed what this is. We already showed that this is mu, but yeah, we'll get to that. All right. So again, we have this green result partially, and then we have the same expansion as we did previously. So this is the expected value of sigma squared set squared plus 2 sigma mu set. I may be doing this way more complicated than necessary, but I'm just going to do it anyway. Minus mu squared. All right. Beautiful. So what happens here? Well, use the linearity again. Still have some time. That's pretty good. So it's going to be sigma squared expected value of set squared plus 2 sigma mu expected value of set plus mu squared minus mu squared. All right. The expected value of set is 0. The mean of the standard normal distribution is 0. It's symmetric about the y-axis. These is 0 and these two cancel. So all that's left is to show that this is 1. And this is slightly tricky, so I hope I can get it. All right? So let's try that out, okay? So the expected value of set squared is equal to the integral of set set times phi of set squared. I'm going to try this. Let's see where it goes. Something like this. I think that's what it is. Yes. All right. So what we use now is that if we actually, if we if we take the standard normal distribution, which is to say where we remove this sigma and these mu, so it just says minus x squared divided by 2, and we differentiate that. You can check this in another section. You differentiate the standard normal PDF, you get x times itself, or minus x times itself. What that means is what this actually is minus the integral of set phi prime of set dz. So I've taken one of these sets and this one and written it as the derivative. You can check that this is true. I don't have time to go through that. You can check that website as well. All right? So we have that. And now we can perform this amazing partial integration. All right? So we get minus set phi set, and then we get minus minus, which is plus, and then we get set differentiated with respect to set, and then phi of set dz. All right, what happens when I differentiate set with respect to itself? Well, it's just 1. All right, and what happens when I integrate the PDF over the whole domain? Well, I just get 1. So this whole thing just becomes 1, and this thing cancels because it vanishes at both infinity and minus infinity. So what I've just shown is that this thing is actually just 1. The expected value of set squared, not maybe super surprisingly, is still 1. Even if I square the normal distribution, the expected value is still 1. And since I showed here that the expected value of x is sigma squared times this actually also just goes to 1. And that's the last result. I'm still not 100% sure on this. Again, probability theory is not my main subject within math, but it looks good, it feels good, and I'll write it in the comments or in the description if I figure out what I feel like feels missing. All right. If you have any questions or comments, leave below.